In this video, we're going to look at complex numbers. We're going to express square roots of negative numbers as a multiple of I being a complex number. We're going to define what I means in terms of numbers. We're going to plot complex numbers on the complex plane. We're going to add and subtract, multiply and divide complex numbers. So the first thing we're going to do is start up with a nice little warm-up about looking at exponents. So when we are looking at these two numbers, 4 raised to the negative 2 and 4 raised to the 8, there's a multiplication symbol between them. These have the same base, they're a base 4. And what that means is that I can add or subtract exponents as appropriate if my bases are the same. So this simply becomes 4 to the negative 2 plus 8. In other words, 4 raised to the positive 6. And if I want to, I can expand that out, or I'm totally fine with leaving it as 4 raised to the 6th. When I have an exponent outside of the parentheses, the exponent actually will distribute onto both the numerator and the denominator. Right now, what you don't see is a raised to the 1 and b raised to the 1. So when I do this, this is a power-to-power exponent rule. I'm actually going to take 5 and multiply it by 1. The reason I say that is because if that was a 2, then I would not add these. I would actually multiply these and multiply 2 and 5 and get 10. But these are both 1s because you don't see an exponent there. So I'm going to go ahead and distribute this by multiplying the 5 on the 1. So I have a to the 5th, and multiplying the 5 and the 1 on the b, so it's b to the 5th. That's as good as that gets. On the next example here, I'm going to do the multiplication of negative 2 and 3. Neither one of those have an exponent on them, except for the fact that there's this 3 that needs to distribute first. So I'm going to go ahead and distribute that 3 exponent through. So I'm going to get negative 2 raised to the 3rd power. I'm going to get x raised to the, and this time because it is a 2 and a 3 here, I do not add them, I multiply them. It's power to power. So 2 multiplied by 3, which gives me x to the 6th and y to the 9th. Now, you're going to think, why did I put the negative inside of parentheses? Well, because it's a negative number, and the exponent is an odd, so it will be a negative answer. But if it wasn't, if that exponent would have been an even number, then it would have actually been a positive number. So the reason I do that is just to make sure that I pay attention to whether or not my answer will be negative or positive. I don't have an exponent on the outside of the second grouping, so this parenthesis does not have an exponent, so I can just go ahead and just rewrite that as 3x raised to the negative 5 and y. Negative 3, or negative 2 to the 3rd power is negative 8, multiplied by that positive 3 gives me a negative 24. And now I'm going to add the exponents on the bases of the x. So I have 6 minus 5. So that ends up becoming x raised to the 1. And I have y to the 9th, y to the 1. I'm going to add those, and I'm going to get y to the 10th. Now I'm going to multiply as expected. When I multiply this x and this x, I'm going to distribute this through, and I'm starting to get x squared. Oops. X squared. So this is going to give me x squared. When I multiply this x and this 3, I'm going to get a minus 3x. When I distribute this negative 3 and this x, I'm going to get a, well, that one should have been positive. This is a negative 3x. And then when I multiply this negative 3 and this positive 3, I end up with a negative 9. These two middle terms, they will cancel themselves out, and so I end up with x squared minus 9. So this is the difference of squares. And you're like, well, I knew that. Why did you have to go through that? Well, it's just as a refresher. So since I know this is the difference of squares, the square root of 5, I see them in the first position of both factor. I see a positive and a negative a in the second position. I know this is the difference of squares. The difference of squares is the first term squared. So I have the square root of 5, the quantity squared, minus a, the quantity squared. But the square root of 5 squared is just 5, so it's 5 minus a squared. We're going to talk about the number system very, very briefly. So we're going to start out with the smallest set, which is the natural numbers. The natural numbers actually does not include 0, so it's actually the natural numbers are contained within the whole numbers, and the whole numbers have a 0 that's in the number set. So natural numbers are the counting numbers, 1, 2, 3. Whole numbers include the 0. Integers, noted with a Z, are the numbers -1, -2, -3 on down, and also including 0, 1, 2, 3 on up. When I get into the rationals, which are symboled with a Q, I start to end up with fractions or decimals that repeat. So 0.3 repeating would be a rational number. Then there's algebraically real numbers, so like the square root of 2 and the negative square root of 3 and 1 plus the square root of 5 all over 2. These are all irrational. Then I go out further and I go into the real numbers and I start picking up pi and the number e, which we will learn if you haven't already learned so. And these are called transcendental numbers, the real numbers in this region here. And then the last set is complex, or also known as imaginary numbers. We define I, the number I, as a square root of -1. Now, complex numbers contain everything inside of them, but a natural number is not necessarily, or a complex number is not necessarily a natural number. So going outwards, natural numbers are contained in integers, contained in rational, contained in algebraic real, contained in real, contained in complex. But going backwards, going in, complex numbers are not necessarily real numbers unless they have a complex number of 0i. So going back in doesn't happen as often or as well as when you're going outwards. Now, why do we care? Well, because a fundamental theorem of algebra says for every polynomial of degree n, there is at least 1 0 in the set of complex numbers. So what does this mean in your own words? I'll let that be yours. So if we look at this number, I have x squared plus 1, and we talked about this a little bit in class, that x squared plus 1 is the sum of squares, because both x squared is positive and 1 is positive, but it doesn't actually factor over the real numbers. Can I factor it? Yes, I can absolutely factor it, but I'm going to factor it with complex numbers. The other way I know that this doesn't factor over the reals is if I look at the graph of this shape. We know from chapter 1.7 that this is a transformation of the graph x squared, and then I've just added 1 to it. So it is the parabolic shape with a transformation of a vertical shift of 1. We can still factor it even though it's not going to cross the x-axis. So here is how we're going to define what a complex number should be wrote as the form of a plus bi, where a is the real part and bi is the complex. So when I said that I can write a real number as a complex, that meant that I had 0 as the b. So if b is 0, then it is a real number, and if a is 0, it is a complex number, and it's also called a pure imaginary, and imaginary numbers are even roots with negative exponents. This is how we define I. I is the square root of -1, and I squared is -1. So now we're going to express each of these numbers here in terms of I. So I have to deal with this negative first. I'm going to write this as -1 multiplied by 9, which is the square root of -1 multiplied by the square root of 9, which gives me square root of 9 is 3, and I is behind it. This is how we normally write it because this is the form that we write. So if I wanted to write it as a complex number, if it's required to write this as a complex number, I would write this as 0 plus 3i. Now I'm going to do the same thing here. So I want you to pause this and I want you to try B and C and then come back. Now if you came back and you said that this is 5i, you would be correct. If you came back and wrote this as a square root of 7i, that'd be correct. But I have a tendency to lose my I underneath the square root, so I will almost always write the I first before the square root so that I don't lose it and try to put it back underneath. Now, how do we do something like this? We'll have I to the 7th or I to the 83. Well, what I know is that if the square root of -1 is I, and then -1 is I squared, then -1 multiplied by the square root of -1 must be I to the 3rd. So in other words, this must be -I. Negative I multiplied by I is going to be I to the 4th. And that's because -I is I to the 3rd, I is I to the 1. So if I were to add these exponents, I'd have I to the third, I to the 1 gives me I to the 4th. So this ends up giving me a negative I squared, but we know I squared is negative 1, so this is a negative 1, which gives me just 1. Oh, I'm at 1. So then I to the 4th multiplied by I must be I to the 5th, which is just going to be I to the 4th is 1 multiplied by I. So this is just I. So I'm actually back to where I started from. Now I know, since I'm back to where I started, I can figure out any power of I as long as I write it as a multiple of 4 and then something else. So let me erase this. Let me move on over here. I have no idea why that's not erasing, so let me try it again. Let me just erase that to get it out of the way. Okay, so I'm going to write I to the 7th as the closest multiple of 7 without going over. So that would be I to the 4th multiplied by I to the 3rd. Well, I to the 4th is just 1. I to the 3rd is negative I. So my answer is just negative I. Similarly, 83, this is I to the 4th raised to the 20 power, because that gives me 80, multiplied by I to the 3rd. I to the 4th raised to is 1. 1 raised to any power is 1. Multiplied by I to the 3rd, but I to the 3rd is just negative I. And that's how you do those when you have high numbers. You write it as a multiple of 4 raised to some power, and then whatever's left over. This is 4 times 20, which is 80, plus 3 gives me the 83. When I'm asked to add, subtract, multiply, or divide complex numbers, I need to, with the adding and subtracting, it's straightforward. I need to add and subtract like terms. What I mean by that is this term and this term are both like, so I'm going to add those two numbers and I get 8. And this term and this term are like numbers, so I have 2i minus 3i, which gives me negative I, and that's my answer. Now with subtraction, it's the same kind of thing. I'm going to take negative 4 and I'm going to subtract off a negative 6. Or actually, I'm going to subtract off a negative 6. So in other words, this becomes a negative 4 minus a minus 6, or negative 4 plus 6, which is just 2. Similarly, I'm going to do these two. This is 4i minus a negative 9i, because it's minus a positive. So this part is going to give me a negative 5i, and so my final answer for this is going to be 2 minus 5i. Easy peasy lemon squeezy. Add like terms, or subtract like terms, and make sure you pull the negative through as appropriate. The multiplication is just as straightforward. I'm going to distribute this 3i here and here. So I'm going to distribute the 3i onto the 5. I'm going to multiply like terms, which gives me 15i. And then I'm going to multiply the 3i and the negative 2i, which is going to give me negative 6. The i's are going to square, just like it'd be x squared. But I squared is negative 1, so this is 15i minus a negative 1 multiplied by 6. So this becomes 15i plus 6. And if I were to write this in the appropriate a plus bi form, I would write this as 6 plus 15i. So now it's in the appropriate form. And with d here, I'm going to distribute as well. So I'm going to distribute the negative 1 onto each one of those two terms. I'm going to distribute the 2i onto each one of those terms. And when I do that, just as before, when I started out with the distributions, when I was looking at x minus 3 and x plus 3, I'm going to just distribute. And so 2 negatives gives me a positive 2. Negative 1 multiplied by a negative 2. Negative 1 multiplied by a positive 3i gives me negative 3i. That gets rid of that multiplication. I'm going to do 2i and negative 2, which gives me negative 4i. And then I'm going to multiply 2i and positive 3i, which gives me positive 6i squared. Now I'm going to deal with anything I need to deal with. So what I mean by that is I'm going to have 2. I'm going to add and subtract the appropriate i's, which gives me negative 7i. And then, of course, 6i squared is the same thing as plus 6 multiplied by negative 1. So now what I really have is 2 minus 6, which gives me, when I do 2 minus 6, I'm going to get negative 4 minus 7i, and that is my final answer. When I'm asked to do division of complex numbers, When I see a complex number in the denominator, what it really is a square root. So when they're asking me to do division of complex numbers, what they're asking me to do is rationalize the denominator. The way I'm going to rationalize the denominator is I'm going to multiply by whatever I need to get rid of the square root in the denominator. In this case, just happens to be I. Numerator and denominator. This would be saying, as an example, if this would have been negative 5 plus 3, the square root of 7 over the square root of 7, actually 2 times the square root of 7, I would have multiplied the numerator by the square root of 7, and I would have multiplied the denominator by the square root of 7. And then what that would have done is eliminated the square root part and done my rationalization. Similarly, I'm going to do that here, and so when I distribute out of the numerator, I'm going to have negative 5i and then plus 3i squared. In the denominator, I'm going to get 2i squared. In the numerator, this is negative 5i. And if you're like this point, I know when I see I squared, it changes the sign, so this is going to be minus 3. And then the denominator, I'm going to have a minus 2. But this is not in the appropriate form. The appropriate form, again, is a plus bi. So I'm going to rewrite this as negative 3 minus 5i all over 2, and then I'm going to distribute the 2 underneath each one of those two terms, which gives me negative 3, negative 3 over 2 minus 5 over 2i. Now it's in the appropriate form. Now, how do we do b and c? Well, the way that we do b and c is we multiply by its conjugate. That's why we did the difference of squares up above. That eliminated that middle term. So we're going to do this by its what we call the complex conjugate. The complex conjugate is exactly the same thing with a 4 here and a 3i here. Since this is plus, I'm going to make that a minus. I'm going to make sure that I distribute on the numerator and the denominator. I'm going to distribute through, and so I'm going to get 8 minus 6i minus 12i plus 9i squared. Let me make that 9i squared. And then in the denominator, since this is the difference of squares, it's going to be the first term squared, which is 16, minus the second term squared, which is 9i squared. In the numerator, I know that 9i squared positive becomes a negative, so I have this 8 right here. I have this 8. And that ends up becoming a negative 9, so that's going to produce a negative 1. And then, of course, I'm going to add the 6 and the 12, which is going to give me negative 18i. And then in the denominator, since I know this is going to change the sign with the I squared, so it's going to be 16 plus 9, that gives me 25. So writing this in the appropriate manner would be negative 1 over 25 minus 18 over 25i. And that's my final answer. I want you to try C. Put this on pause. Go ahead and try C. See if you can get the answer. Welcome back. Hopefully the answer that you got when you got done is negative 5 over 13 plus 12i over 13. And complex conjugates we just talked about. They are basically the same thing, negative 3, 7i, 7i. The difference is one's a positive and one is a minus. When you multiply two complex conjugates, your answer is always a real number and it's always positive. So if I'm asked to find the complex conjugate and then multiply, we know from up above and here that this is going to be 4 minus 5i. We also know that at the end of the day, this is going to be 16 minus 25i squared, which I squared becomes negative 1, so it's 16 plus 25. And then I just add those two together, and I'm going to get 41. Similarly, I know this is negative 2 plus 3i. I'll let you finish that. And this is going to be negative 9i. Because what really here is 0 plus 9i. And then 0 minus 9i. And I'll let you finish those off. True or false, or give her a counter example. The conjugate of a product is the product of the conjugates of individual complex numbers. Let you think about that. The sum of two numbers that are conjugates of each other is always a real number. So if you add two conjugates together, is it always a real number? And the conjugate of the sum of conjugates of the individual complex number So those are all things I want you to do, true or false, or give counter examples. Lastly, if I am asked to solve. So the reason that we learn this is so that we can solve polynomials, and realizing that sometimes when we solve polynomials, we get complex numbers as answers. So I'm going to take the square root of both sides, and so for this first one here, I'm going to have x squared, the square root, is equal to the square root of -8 plus and minus. So x is equal to plus and minus I, the square root of 8, by taking the negative out, which I'm going to simplify a little bit. Since 8 is the same thing as the square root of 4 multiplied by 2, this is going to be plus and minus 2i, the square root of 2. The next one, similar kind of thing, is I'm going to do this as 2x squared is equal to -50. And then x squared is going to give me -50 divided by 2, solving for x squared. Coming over here, I'm going to get x squared is equal to -25. And so x is going to be equal to plus and minus 5i. That's by taking the square root of 25 and the square root of -1. 5i. Now, this last one, what this last one does, if you do just this step, you have x to the 4th is equal to 1. Taking the 4th root of both sides, x is equal to plus and minus 1. However, if you do that, you are losing some of the solutions. Because what this is x squared minus 1 is equal to 0. So this factors in the difference of squares. This becomes x squared minus 1 and x squared plus 1 is equal to 0. Well, we know this is just going to give us x is equal to positive and -1, and then this one ends up giving us x is equal to positive and -1i, or just I. Oh, I don't have any complex. So let's graph some of these on the complex plane. So not the solutions, but the complex. I said I was going to graph these, and for some reason I don't have it here, so let's just talk about it. So when we're graphing in the complex plane, this is the real part, this is the imaginary part. So if I wanted to do a plus bi, then I'd come along here a, and I'd come along here in the b direction. So as an example, if I was asked to do 3 minus 2i, I'd go over here to 3, I'd go down to -2i, and right here would be my point, 3 minus 2i. So the complex plane looks a lot like the real plane, the Cartesian xy plane, with the exception of, as it's not wrote as an ordered pair, it's wrote as 3 minus 2i, or whatever the case may be. And that's it for this video. Fairly short, fairly sweet, and if you have questions, bring them to class.